Good day, everybody. How are you all? Today we are going to discuss about sampling and data. So here I go. So this is a chapter on sampling and data. So the science of statistics deals with collection, analysis, interpretation, and presentation of data. We see and use data in our everyday lives. So you wonder what is data all about? Data are pieces of information. Data is the plural form of datum, which means information. In this course, you will learn how to organize and summarize data. Organizing and summarizing data is called descriptive statistics. Now, the word descriptive comes from the word description, so you are describing the characteristics of the data or pieces of information that you have collected. Two ways to summarize data by graphing and by using numbers. For example, finding an average. After you have studied probability and probability distributions, you will use formal methods for drawing conclusions from good data. The formal methods are called inferential statistics. The word inferential comes from the word inference, which means to draw a conclusion. You will draw a conclusion about a population characteristic. Now, population includes the entire population. Sometimes we have to draw a conclusion on a population characteristic based on information from the sample that is a part of the population. This type of statistics is called inferential statistics. Statistical inference uses probability to determine how confident we can be that our conclusions about the population are correct. So probability is the likelihood of something happening or chance of something happening. Probability is a mathematical tool used to study randomness. Randomness means without any preference, without any particular order. It deals with the chance, the likelihood of an event occurring. The expected theoretical probability of heads in any one toss is half or 0.5. Why, you ask? Because there is one head out of two faces in a coin. What are the two faces? One is a head, one is a tail. So the probability of a head in the long run, getting a head when you toss a coin, is half or 0.5. Even though the outcomes of a few repetitions are uncertain, there is a regular pattern of outcomes when there are many repetitions. Now, pattern of outcomes means pattern of results. That means when you toss the coin 10 times, you do not expect to get 5 heads and 5 tails. However, if you toss the coin, say 10,000 times, you may get half heads and half tails. Okay, so there's a pattern in the long run to get half heads and half tails. Long run means tossing the coin long number of times. For example, if you toss a fair coin 4 times, the outcomes may not be 2 heads and 2 tails. However, if you toss the same coin 4,000 times, the outcomes will be close to half heads and half tails. So if we increase the number of times you are tossing the coin, and then in that case, you can expect half heads and half tails. In statistics, we generally want to study a population. Population means the entire collection of people. Say the population of students at a college. You can think of population as a collection of persons, things, or objects under study. The statistic is an estimate of a population characteristic. Notice in this, the statistic, there is no S at the after C in the last letter. It is just statistic. It means an estimate of the population parameter. What is a population parameter? Parameter is a characteristic of the population. A parameter is a number that is a property of the population. So we use a sample statistic. A sample characteristic is called statistic without the S at the end. From that sample statistic, we can make an estimate of the population characteristic or population parameter. Notice population begins with letter P, parameter also begins with letter P. Similarly, sample begins with letter S, statistic begins with letter S. Since we considered all math classes to be the population, then the average number of points earned per student over all the math classes is an example of a parameter. Since we included all the math classes, that will be a population characteristic, hence that's a parameter. To study the population, we select a sample. You ask why? Because it's very hard to reach the entire population of, say, the students at a college. The idea of sampling is to select a portion or subset, means a part of the population of the larger population, and study the portion, the sample, to gain information about the population. For the sample data, we can calculate a statistic. A statistic is a number that represents the property of a sample. Like I said before, S statistic begins with letter S, sample also begins with letter S. So characteristic of the sample is sample statistic. For example, I may collect a sample of students from all the statistic students at the college. And then I might ask my sample, what is your age at your last birthday? I will ask each student in the sample, what is your age at the last birthday? Okay, I say I have 50 students in my sample. I can get 50 answers from my survey. I will add up all the 50 numbers of ages, divide by 50, I get a sample mean age. That is a statistic. For example, if we consider one math class to be a sample of population of all math classes, then the average number of points earned by students in that one math class at the end of the term is an example of statistic. Okay. Sample characteristic is sample statistic, whereas a population characteristic is population parameter. Data are actual values of the variable. So data is a plural form. There may be numbers or there may be words. So datum is a single value. So datum is a singular version of data. Data are the result of sampling from a population. Because it takes a lot of time and money to examine an entire population, sampling is a very practical technique. One of the main concerns in the field of statistics is how accurately a statistic estimates a parameter. The accuracy really depends on how well the sample represents the population. Now, you might ask me, what is accuracy? Accuracy in this case means how the sample characteristic or the sample statistic, how close it can come to the population parameter or population characteristic. That is accuracy. Now, if your sample is representative of the population, there's a good chance that the sample statistic will be close to the population parameter. The sample must represent the characteristics of the population in order to be a representative sample. We are interested in both the sample statistic and the population parameter in inferential statistics. As a matter of fact, we will use the sample statistic to predict or forecast the population parameter using the techniques that we will learn in inferential statistics. Inferential, as you can think, comes from the word inference, which means to draw conclusion. Here we are going to draw conclusions about the population characteristic or parameter based on sample characteristic or statistic. Okay. A variable noted by a capital letter such as capital X and capital Y is a characteristic of interest for each person or thing in a population. Variables may be numerical or categorical. Okay. So what is a variable? Okay. It can be numerical or it can be categorical. What is an example of numerical? What is your age at your last birthday? It's a number. So it's numerical. Okay, numerical variable. But if I categorize student in my class at male and female, okay, male is a category. It's a categorical variable. Numerical variables take on values with equal units, such as weight in pounds and time in hours, or age in years. Categorical variables place the person or thing into a category, such as the two genders of the students in my class, male and female. There are two categories of genders. Two words that come up often in statistics are mean and proportion. The word mean and average are often used interchangeably. The substitution of one word for the other is a common practice. The technical term is arithmetic mean, and average is a technically a center location. That is, where is the center of the data set. However, in practice among non-statisticians, average is commonly accepted for arithmetic mean. Determine what the key terms referred to in the following study. A study was conducted at a local college to analyze the average cumulative GPAs of students who graduated last year. Okay. Fill in the letter of the phrase that best describes each of the items below. Okay. So, part A, all students who attended the college last year is a population. The cumulative GPA of one student who graduated from the college last year, that is a sample statistic. Okay. These are GPAs of 4 students, part C. So it's sample statistic. A group of students who graduated from the college last year is randomly selected, that is sample. The average cumulative GPA of students who graduated from the college last year, I presume of all students, so it's a population characteristic, so it's a parameter, part E. Part F, all students who graduated from the college last year, that's a population. And part G, the average cumulative GPA of students in the study who graduated from the college last year. Okay. And again, I presume that is all students, therefore it's a population characteristic, therefore it is a parameter. Determine what the key terms referred to in the following study. We want to know the average mean amount of money spent on school uniforms each year by family with children at Knoll Academy. We randomly survey 100 families with children in the school. 3 of the families spent $65, $75, and $95. These are all sample characteristic, and 100 families is only a sample or subset of the entire population of families who have students at Knoll Academy. So these three numbers, 65, 75, and 95, are sample characteristic. So these are statistic. Okay. Data, sampling, and variation in data and sampling. In this section, we will classify data as qualitative or quantitative, classify data as continuous, discrete, or neither, determine types of graphs appropriate for specific data, identify the basic techniques for choosing samples. Qualitative data are a result of categorizing or describing attributes of a population. Categorizing means dividing the population into categories. Hair color, for example, blood type, OH, B, A, O, all these are blood types. Ethnic group, Asian, African, these are all ethnic groups. The car a person drives, Toyota, Mercedes, these are all categories. And the street names are categories. Living are examples of qualitative data. Qualitative data are generally described by words or letters. Quantitative data comes quantitative, as you can think, the word comes from quantity, how many or how much, and they're represented by numbers. Quantitative data are the result of counting or measuring attributes of a population. Attributes means characteristics of a population. amount of money, pulse rate, weight, the number of people living in your town, number of students who take statistics are example of quantitative data. Quantitative data may be either discrete or continuous. All the data are the result of counting are called quantitative discrete data. These data take on certain numerical values, such as if I ask a student in my class, how many brothers and sisters you have? Either it has to be 0 or 1 or 2 or 3. So the student lists or counts the number of brothers and sisters. And notice we are jumping from 0 to 1. 1 to 2. We cannot have 1.5 brothers and sisters. So the numbers are counted and listed, and we discretely jump from one number to the other without any decimal value in between. That is discrete quantitative data. All data that are result of measuring are quantitative continuous data, assuming that we can measure accurately. What is your weight? It can be 155.5, it can be 135.6, depending on the accuracy of the scale. But notice I'm measuring with a scale and I'm taking decimal values. Okay. You may note, you may collect data as numbers and report it categorically. For example, the quiz scores for each student are recorded throughout the term. At the end of the term, the quiz scores are reported as A, B, C, D, F. Okay, so these are categorical data. Okay. Data sample of quantitative discrete data. The data are the number of books students carry in their backpacks. You sample 5 students. 2 students carry 3 books, 1 student carry 4 books, and 1 student carries 2 books, and 1 student carries 1 book. The numbers of book 3, 4, 2, and 1 are quantitative discrete data. Notice from 3 we are jumping to 4, from 2 we jump to 3, from 1 we jump to 2. There is no decimal values possible, and we are counting, okay, or listing the number of books carried. This is a quantitative discrete data. Okay, example 1.6, data sample on quantitative continuous data. The data are the weights of backpacks with books in them. You sample the same 5 students, the weights in pounds of their backpacks are 6.2, 7, 6.8, 9.1, 4.3. Notice the backpack carrying 3 books can have different weights. Weights are quantitative continuous data. Also notice you're measuring the weight in decimals. When you measure something, that's a quantitative continuous data because it can take any value in an interval. In this case, for example, if you consider the first 3 data points, 6.2, 7, and 6.8, it takes any value in the interval between 6 and 7. It takes decimal values. Weights are quantitative continuous data. Something that is measured is continuous data. Something that is counted is discrete data. The data are the colors of backpacks. Again, you sample the same 5 students. One student has a red backpack, 2 students have black backpacks, 1 student has a green backpack, and 1 student has a gray backpack. So the colors of the backpacks are red, black, green, and gray are qualitative data. Why? Because these are categorical data, categories of colors. Work collaboratively to determine the correct data type, quantitative or qualitative. Indicate whether quantitative data are continuous or discrete. Hint, data that are discrete often start with the word, the number of pairs of shoes, discrete data. And okay, and it is discrete. Why? Because you cannot have 1.5 pair of shoes, right? So decimal values are not possible, and you are counting or listing. Therefore, it's discrete quantitative data. Type of car you drive, that's category. Okay, because why? You can drive a foreign made car, you can drive an US made car. These are all categories of cars. The distance it is from your home to nearest grocery store, that is measured by the odometer in your car, and it can take decimal values. So it's a continuous quantitative data. Whereas the type of car is categorical qualitative data. The number of classes you take per school year that you list, therefore it's discrete quantitative data. You can take 2 classes, you can take 3 classes. Type of calculator you use can be TI, can be HP. So it's categorical data, categorical qualitative data. Weight some sumo wrestlers, you measure it. So it's continuous quantitative data. Number of correct answers on a quiz, it can be 0, it can be 1, it can be 2, counted or listed. So it's discrete quantitative data. IQ scores, this may cause some discussion because IQ scores may be in whole number, can be in decimal. Okay, if it is whole number, then it is discrete quantitative data. If it can take decimal values, and then it is continuous quantitative data. The data are the number of machines in a gym. You sample 5 gyms. One gym has 12 machines. One gym has 15 machines. One gym has 10 machines. One gym has 22 machines, and the other has 20 machines. What type of data is this? Discrete. Okay, discrete quantitative data. The data are the areas of the lawn in a square feet. You sample 5 houses, the areas of lawn, but you measure the area of the lawn. So it's a continuous quantitative data. The data are the colors of house, categories. So it's a categorical qualitative data. Tables are a good way of organizing and displaying data, but graphs can be even a bit more helpful in understanding data. There are no strict rules concerning which graphs to use. Two graphs that are used to display qualitative data are pie charts and bar graphs. So this is an example of ethnicity of students in percentage. Okay. In pie chart, categories of data are represented by wages in a, so you divide the entire circle into sectors, which are called wages. Okay. For example, on the left, you see there are 36.1% Asian. Okay. In a circle, and are proportional in size to the percent of individuals in each category. Okay, so the categories are represented by different sectors, and the area in each category or each sector represents a percentage in the actual data point, in the actual data, I should say. Okay, ethnicity of students. Okay. So pie chart, why? Because it's a circle, pie, and then divided into different sectors or wages that represent the percentage, okay, of individuals in each category. Same thing can be represented by a bar graph. In a bar graph, the length of the bar for each category is proportional to the number or percent of individuals in each category. So you have the categories of classes of possible students, ethnicity. On the horizontal axis, the vertical axis represents the percentage. The heights of each category is proportional to the percentage of students in each category. So what is the difference between this one and the previous one? Here, the categories are arranged as they appear in the data set. On the next one, the bars will be arranged. Bars of the different categories will be arranged from highest to lowest. This is called a Pareto chart. What is the advantage of this type of chart? Visually more appealing, and you can easily draw conclusions based on looking at these pie charts arranged from the highest to the lowest. A statistics professor collects information about the classification of a student as freshmen, sophomore, juniors, or seniors. The data she collects are summarized in the pie chart in figure 1.3. What type of data this graph shows? Okay. Basically, this shows the percentage of students in each type of categories such as freshmen, sophomores, juniors, and seniors. Actually, the area of which each wages is proportional to the percentage of students in each category of class. So, for example, looking at this pie chart, we can say freshman is constitute the highest percentage of students, followed by sophomore, then it is junior, and finally it is senior. The register at State University keeps records of number of credits our students complete each semester. The data he collects are summarized in the histogram. The class boundaries are 10 to less than 13, 13 to less than 16. So these classes are on the horizontal axis. If you look at the horizontal axis, 10 to 13 is the first class on the horizontal axis, then 13 to 16 is the second class in the horizontal axis, then 16 to less than 19 in the third class. In the fourth class, it's from 19 to less than 22. And in the fifth class, it is from 22 to less than 25. What type of data this shows? You're looking at number of students who have completed what type of credit hours. So for example, if you look at the height of each bar, you know the number of students in each class or group of data. For example, if you look at the first class between 10 and 13 credit hours completed, only 250 students. Whereas you look at 13 to 16 credit hours completed, the height of that particular bar, if you read on the vertical axis, is close to 600, more like 575 number of students. And if you look at the class with the highest height of the rectangle on top of it, is between 16 and 19. And that class is slightly more than 700. I would say 730 students have completed between 16 and 19 credit hours. Okay. So basically the heights of each bar represent the number of students who have completed that particular number of credit hours, and the credit hours are on the horizontal axis divided into 5 groups. Gathering information about an entire population often costs too much or is virtually impossible. Instead, we use a sample of the population. A sample should have the same characteristic as the population it is representing. For example, if I want to find out what is the average age of all students at a college campus, I cannot reach all the students because it's time consuming and costs a lot of money. So instead of that, I will select a sample of students from that campus and ask, what is your age to each student in that sample? Then I will add all the ages and divide by the number of students in the sample. Okay. But the critical thing is that will give me sample mean from which I can predict the population mean. But the critical thing is the sample should have the same characteristic as the population it is representing. There are several different methods of random sampling. Random means without any preference, without any particular order. In each form of random sampling, each member of a population initially has an equal chance of being selected for the sample. So what is a random sample? Each member in that sample has an equal chance of getting selected. The easiest method to describe is called a simple random sample. Simple, process is simple. Random means without any preference or particular order. So what is a simple random sample? Any group of n individuals is equally likely to be chosen by any other group of n individuals if the simple random sampling technique is used. In other words, each sample of the same size has an equal chance of being selected. What does it mean? Suppose you have a college with 5,000 students and I want to select a sample of 50 students. There are many, many samples of size 50 that I can collect from that population of 5,000 students. Okay. The sample that I select will be a simple random sample of size 50. If every sample of size 50 from that population has an equal chance of getting selected. That is, I'm not showing any preference to any particular sample of 50 students. I'm randomly selecting students to be part of my sample from the entire population so that every sample of size 50 from that population has an equal chance of getting selected. True random sampling is done with replacement. What is replacement? That is, once a member is picked, the member goes back into the population and thus may be chosen more than once. However, for practical reasons, in most population, simple random sampling is done without replacement. What does it mean? You select one person from the population to be part of the sample and do not put that person back in the population again to be selected. So basically, once a person is selected to be a part of the sample from the entire population, leave the person in the sample. Do not put him or her back in the population. This is sampling without replacement. In a college population of 10,000 people, suppose you want to pick a sample of 1,000 randomly for a survey. For any particular sample of 1,000, if you're sampling with replacement, the chance of picking the first person is 1,000 out of 10,000. Okay. The chance of picking a different second person for this sample is 999 out of 10,000. You replace the first person before picking the next person. For any particular sample of 1,000, if you are sampling without replacement, the chance of picking the first person for any particular sample is 1,000 out of 10,000. Okay. The chance of picking a different second person is 999. Why now 999? Because the first person selected stays in the sample, does not go back in the population. The total has also decreased by 1. That is why it is 999 out of 9,999. Okay, if you replace the person, you do not replace the person. So in this case, you do not replace the person before picking the next person. That's why both possibility are changing. So when you selected the first person out of 10,000, that person stays in the sample, okay? Then you have only 9,999% left in the population, okay? And your total sample size is still 1,000. You have already selected one person. Therefore, you have to select the remaining 999 persons out of a total population now consisting of 9,999 people. Because you have reduced one person from the entire population, that person stays in the sample, the population size decreases now. So how to use a TI-8384 calculator to generate a list of random numbers is shown here. Okay. Besides simple random sampling, there are other forms of sampling and involve a chance process for getting the sample. Other well-known random sampling methods are stratified sample, the cluster sample, and the systematic sample. To choose a stratified sample, divide the population into groups called strata and then take a proportionate number from each stratum. Okay. What is an example of that? If you are sampling students from a college, you can divide the students into strata or groups of freshman, sophomore, junior, and senior, depending on number of credits completed. Then you randomly select students from each strata, okay, from each stratum. To choose a cluster sampling, divide the population into clusters, groups, and then randomly select some of the clusters. All members from these clusters are in this cluster sample. What is an example of that? You can divide a city into zip codes, and there may be 10 zip codes in the big city, and you only select 2 zip codes and then interview each person in those selected 2 zip codes. That you dividing the city into zip codes, those are clusters, and then you select 2 clusters randomly and then interview every member of those 2 selected clusters. This is a cluster sample. To choose a systematic sample, randomly select a starting point and take every nth piece of data from a listing of the population. A type of sampling that is non-random is convenience sampling. That is not good. Convenience sampling services involves using results that are readily available. So you're using some sample because they're readily available. When you are analyzing data, it is important to be aware of sampling errors and non-sampling errors. The actual process of sampling causes sampling errors. For example, the sample may not be large enough. That is a that can cause sampling error. Factors are not Factors not related to the sampling process are called non-sampling errors. A defective counting device can cause a non-sampling error. In statistics, a sampling bias is created when a sample is collected from a population and some members of the population are not as likely to be chosen as others. Remember, each member of the population should have an equal likely chance of being chosen. If that is not the case, then we have a sampling bias. When a sampling bias happens, there can be incorrect conclusions drawn from the population that is being studied. Variation is present in any set of data. For example, 16-ounce cans of beverage may contain more or less than 16 ounces of liquid. It was mentioned previously that two or more samples from the same population taken randomly and having close to the same characteristics of the population will likely be different from each other. Okay. So two samples or more samples taken from the same population, if we done random selection, and having close to the same characteristics of the population will likely. For example, if I select a sample randomly of students from a population, say sample size is 50, population size is 5,000. I ask those 50 students, what is your age at last birthday? 50 numbers, add those 50 numbers, divide by 50, I get a sample mean of say 21.2 years. The next sample, I may get the sample mean as 22.5 years. Okay. So there's sample to sample variation. Okay. Determine the type of sampling used: simple, random, stratified, systematic, cluster, or convenience. A soccer coach selects 6 players from a group of boys aged 8 to 10, 7 players from a group of boys aged 11 to 12. So the first group of boys selected were from aged 8 to 10. The second group of players is from boys aged 11 to 12. 3 players from a group of boys aged 13 to 14 to form a recreational soccer team. It looks like the soccer players was divided into strata based on their age. So this is a stratified sampling. A poster interviews all human resource personnel in 5 different high-tech companies. Okay. 5 different high-tech companies. Okay. So not all high-tech companies were selected, only 5 different high-tech companies were selected. So this is cluster sampling. A high school educational researcher interviews 50 high school female teachers and 50 high school male teachers. Again, high school teachers were divided into 2 clusters. Okay. Male and female. A medical researcher interviews every third patient, cancer patient. So it is systematic. A high school counselor uses a computer to generate 50 random numbers and then pick students whose names correspond to the numbers. This is simple random sampling. Okay. And a student interviews classmates in his algebra class to determine how many pairs of genes a student owns on the average. This is convenience sampling. Determine the type of sampling used, simple, random, stratified, systematic, cluster, or convenience. A high school principal polls 50 freshmen, 50 sophomores, 50 juniors, and 50 seniors regarding policy changes after school for after school activities. Therefore, this has been divided into strata: freshmen, sophomores, juniors, and seniors, four strata or four classes. So it's stratified sampling. Okay. Suppose ABC College has 10,000 part-time students, the population. We are interested in the average amount of money a part-time student spends on books in the fall term. Assuming all 10,000 students is an almost impossible task. Suppose we take two different samples. First, we use convenience sampling and survey 10 students from a first term organic chemistry class. Many of these students are taking first term calculus in addition to the organic chemistry class. The amount of money they spent on books are as follows. Okay. And this is we have this is the convenience sampling. Okay. The second sample is taken using a list of senior citizens who take PE classes and taking every fifth. And so this is systematic sampling. They spend this amount. It is unlikely that any student is in both samples. Do you think that either of these samples is representative or characteristic of the entire 10,000 part-time student population? No, because this is convenience sampling in first scenario. Okay. Since this, and in the second case, it is systematic sampling. So it is also not randomly selected. Suppose these samples are not representative of the entire population. Is it wise to use the results to describe the entire population? The answer is no, because these are either convenience sampling or you have systematic sampling. The sample does not represent the characteristics of the entire population. Okay, so these are non-random samples, therefore it is not wise to use the results of the sample to describe the entire population. Okay. Now suppose we take a third sample. We choose 10 different part-time students from the discipline of chemistry, math, English, psychology, sociology, history, nursing, physical education, art, and early childhood development. We assume that these are only disciplines in which part-time students at ABC College are enrolled and that an equal number of part-time students are enrolled in each discipline. Each student is chosen using a simple random sampling. Using a calculator, random numbers are generated and a student from particular discipline is selected if he or she has a corresponding number. The student spend the following amounts. Because we have randomly selected students, this sample is not biased. So this sample data will give us an idea of a population characteristic. A local radio station has a fan base of 20,000 listeners. The station wants to know if its audience would prefer more music or more talk shows. Asking all 20,000 listeners is an almost impossible task. The station uses convenience sampling and surveys the first 200 people they meet at one of the station's music concert events. 24 people said they prefer more talk shows, and 176 people said they would prefer more music. Do you think that this sample is representative of or is characteristic of the entire 20,000 listener population? No, because this is convenience sampling. A convenience sample does not represent the population characteristic generally. Okay. Now we are going to talk about frequency table, and labels of measurement. In this section, we'll use basic vocabulary to determine the measurements. Okay, let's move on. The way of set of data is measured is called a level of measurement. Data can be measured into 4 levels of measurement. They are from lowest to highest level: nominal scale, ordinal scale, interval scale level, and ratio scale level. Data that is measured using a nominal scale is qualitative. Categories, colors, names, labels, and favorite foods, along with yes or no responses, are example of nominal level data. Categories, names, colors, these are all qualitative data, and these these are representative of nominal scale data. Nominal scale data are not ordered. For example, trying to classify people according to their favorite food does not make any sense. Putting pizza first and sushi second is not meaningful. Smartphone companies are another example of nominal scale data. Again, these are categories: Sony, Motorola, Nokia, Samsung, and Apple. This is just a list, and there is no agreed upon order. Some people may favor Apple, but that is a matter of opinion. Nominal scale data cannot be used in calculation. So now basically what we learned, nominal scale is qualitative data, and these are basically categories, colors, names, labels, etc. You cannot put them in order. Data that is measured using an ordinal scale is similar to nominal scale data, but the ordinal data scale data can be ordered. An example of ordinal scale data is a list of top 5 national parks in the United States. The top 5 national parks in the United States can be ranked from 1 to 5, but we cannot measure differences between the data. Another example of using the ordinal scale is a quiz survey, where the responses to questions about the cruise are excellent, good, satisfactory, and unsatisfactory. These responses are ordered from the most desired response to the least desired, but the difference between two pieces of data cannot be measured. Like the nominal scale data, the ordinal scale data cannot be used in calculation, because you are just putting for example, in the cruise survey, you're putting them in order, but you do not know the exact difference between them. Okay. And these are not numbers, these are just categories of satisfaction. So, but these are arranged in order from most preferred to the least preferred. Therefore, ordinal. Ordinal comes from the word order. Okay, so data in ordinal scale can be ordered. Data that is measured using the interval scale is similar to ordinal level, ordered, because it has a definite ordering, but the differences between the interval scale can be measured, though the data does not have a starting point. Temperature scale like Celsius and Fahrenheit are measured by using the interval scale. In both temperature measurements, 40 degree is equal to 100 minus 60 degree. Difference makes sense, but 0 degree does not make, because in both scales, 0 is not absolute lowest temperature. Temperatures like minus 10F and minus 15C exist and are colder than 0. So 0 does not mean the absence of heat. Okay. On the other hand, we know 40 is lower than 60. Difference between 40 and 60 can be made. Interval level data can be used in calculators, but one type of comparison cannot be done. 80 degrees centigrade is not, 80 degrees Celsius is not 4 times as hot as 20 degrees Celsius, nor is 80 degree Fahrenheit 4 times as hot as 20 degree Fahrenheit. There is no meaning of the ratio of 80 to 20. Okay, so you can do addition, subtraction, but you cannot take ratio in interval level of measurement, interval in data that are measured using interval scale. Oops, what happened? Data that is measured using the ratio scale takes care of ratio problem and gives you the most information. Ratio scale data is like interval scale data, but it has a 0 point, and ratios can be calculated. Okay, for example, 4 multiple choice statistics final exam scores are 80, 68, 20, and 92 out of a possible 100 points. The exams are machine graded. The data can be put in order from lowest to the highest, 20, 68, 80, and 92. The difference between the data have meaning. The score 92 is more than score 68 by 24 points. Ratios can be calculated. The smallest score is 0, so 80 is 4 times as much as 20. The score of 80 is 4 times better than score of 20. So bottom line, you can add, subtract, you can divide, you can take ratios in the ratio level measurement, ratio scale, data that are measured in ratio scale. So ratio scale is the highest level of measurement. Frequency is the number of times a value of the data occurs. The sum of the values in the frequency column uh, represent the total number of values included in the sample. So frequencies count basically. Frequency comes from the how frequently, comes from the word frequently. So frequency is a count. Relative frequency is the ratio, fraction or proportion of the number of times the value of the data occurs in the set of all outcomes. Outcomes again mean results to the total number of outcomes. So basically, relative frequency is the frequency or the count in each category divided by total number of frequency. To find the relative frequency, divide each frequency by the total number of data values. Relative frequencies can be written as fraction, percents, or decimals. Cumulative relative frequency is the accumulation of the previous relative frequencies. To find the cumulative relative frequencies, add all the previous relative frequencies, okay, to the relative frequency for the current row, okay. Because of rounding, the relative frequency columns may not be always summed to 1, and the last entry in the cumulative relative frequency column may not be 1. However, they each should be close to 1. So here is an example of relative frequency. First, they have the heights in different groups. Like for example, the first group is or class is between 59.95 and 61.95, and there are 5 people in that height. So frequency or count in that class is 5. Now, if you add up all the frequencies, the total number of counts or total size of the sample is 100. So relative frequency in the first class is 5 out of 100 or 0.05. And the cumulative relative frequency on that class is 0.05. What is the meaning of the word cumulative? Comes from the word accumulate. You not only take the frequency of that class, which is 0.05, and anything above it, but there's nothing above the first class. So the cumulative relative frequency is 0.05 in the last column, in the first row. You go to the next row, the class is between 61.95 and 63.95. Count in that class is 3. So relative frequency is 3 out of 100 or 0.03. Now cumulative relative frequency, you take 0.03 and add the class on top of it, which is 0.05, 0.03 plus 0.05 is 0.08 in the third column, second row. And you continue in this way. Okay. For table 1.1, to find the percentage of height that are less than 65.95. Less than 65.95 is, so you see in 1, 2, 3, 4, 5th class, less than, so up to the 5th class ends at 69.95. Okay. So anything less than 69.95, cumulative relative frequency is 0.8 in that row, which is the 5th row, 3rd column. So 80% of the people are less than 69.95. Okay. And you can do the other things. The results are shown here. And then there's another table, 1.13. These are rainfall inches. So let's do the first one from table 1.13, which is the previous table. Find the percentage of rainfall that is less than 9.01. So less than 9.01 means up to the 3rd class, because the 3rd class ends at 9.01, and the cumulative relative frequency in the 4th column, 3rd row is 56. What does it mean? 56% of the cumulative of the frequency of the rainfall is less than 9.01 and so forth. Okay. What is the frequency of the deaths measured from 2006 to 2009? Let me go to the, oops, I do not want that. I want to go to the, what is the frequency of deaths measured from 2006 through 2009? So you add up the numbers, 6,605 plus 712 plus 88,011 through 2009. Therefore, you have to add the fourth number also, which is 1790. Okay. And you can do the other calculations. Okay. Experimental design and ethics. The purpose of an experiment is to investigate the relationship between two variables. Again, remember, variables come from the word vary. It's a characteristic which varies from person to person or from object to object in a sample. When one variable causes change in the other, we call the first variable the explanatory variable. Okay. This is sometimes also called the independent variable, and usually this variable is represented on the horizontal axis or x-axis. The affected variable is the response variable, sometimes also called the dependent variable, which is represented on the vertical axis or y-axis. In a randomized experiment, the researcher manipulates values of the explanatory variable and measures the resulting changes in the response variable. So independent variables values are changed and the response on the resulting and the response of the resulting changes in the y variable or the dependent variable are measured. The different units, the values of the explanatory variable are called treatments. An experimental unit is a single object or individual to be measured. Okay. Additional variables that can cloud a study are called lurking variables. In order to prove that explanatory variable is causing a change in the response variable, that is, the independent variable change is causing a change in the dependent variable, it is necessary to isolate explanatory variable. The researchers must design the experiment in such a way that there is only one difference between the groups being compared, the planned treatments. This is accomplished by random assignment of experimental units to treatment groups. So, for example, if I want to test a new drug, I will first recruit volunteers. Then I'll divide the volunteers into two random groups. What is random group? Each volunteer will be randomly assumed in either group A or group B, two groups A and B. So each volunteer has an equal chance of getting selected either in group A or group B. Once the volunteers are randomly placed in group A or group B, then I control what type of drug I give to them. In group A, for example, I can give the actual test drug. In group B, I get a sugar pill, placebo. Okay. So why do I do that? So that the effect of the study or the effect of the new drug comes out clear, whether it is able to reduce the disease or illness which is supposed to do. Okay. This is accomplished by random assignment of the experimental units, that is, in this case, volunteers to the treatment groups. What is the treatment groups? One group is getting the actual drug, the other group is getting the placebo. But they will not know for sure which particular drug they are getting, because the two drugs are the shapes and sizes and the colors will be exactly identical. When subjects are assigned treatments randomly, all of the potential lurking variables are spread equally among the groups. When participation in a study prompts a physical response from a participant, it is difficult to isolate the effects of explanatory variable. To counter the power of suggestion, researchers set aside one treatment group as a control group. In my example, the control group is the group that was getting the placebo medicine, which is sugar pill. This group is given a placebo treatment, a treatment that cannot influence the response variable. So if it is a placebo, it cannot cure the disease, right? The control group then helps researchers balance the effect of being in an experiment with the effects of the active treatments. Of course, if you are participating in a study and you know that you are receiving a pill which contains no actual medication, which is the placebo, then the power of suggestion is no longer a factor. Blinding means you are not going to tell who's getting what pill. Blinding in a randomized experiment preserves the power of suggestion. When a person involved in a research study is blinded, he or she does not know who's receiving the active treatments and who's receiving the placebo treatment. A double-blind experiment is one in which both the subjects and the researchers involved with the subjects are blinded. That is, neither the person who has been selected in a study in a group knows what pill he or she is getting, nor do the researchers who are administering or giving the pill to the subject knows what pill he or she is giving. The widespread, the widespread misuse and misrepresentation of statistical information often gives the field a bad name. Some say numbers don't lie, but the people who use numbers to support their claims often do. Many types of statistical fraud are difficult to spot. Some researchers simply stop collecting data once they have just enough to prove what they have had hoped to prove. They don't want to take the chance that a more extensive study would complicate their lives by producing data contradicting their hypothesis. What is an hypothesis is an educated guess. So they'll stop taking data once they have collected enough data to show that their hypothesis or educated guess is true. This is not ethically correct way to do experiments. Okay, so we will stop here today. If you have any question or comment, write me a note. I'll get back to you as soon as possible. If you like this video, please give me thumbs up. I'll appreciate that. If you like this video, please share with your friends. You and your friends, please subscribe to my channel by hitting the red subscribe button at the bottom right corner. I'm back every day with new problem, new solution, new material. So please do not forget to check me out tomorrow. Thanks for watching. Have a nice day. Take care. See you next time.